Welcome to episode 131, Spotlight, System Recovery and Reconstitution, where we explore how organizations rebuild systems cleanly and resume their mission after a major disruption. The CP-10 control emphasizes that restoration is more than restarting servers. It is about regaining trust in the environment and ensuring that no hidden contamination remains. Recovery and reconstitution together define a disciplined process of returning from failure to a verified, fully functional state. This control ensures that systems are rebuilt from known good sources, validated step by step, and approved before reconnecting to production networks. A deliberate, methodical recovery turns chaos into order and restores both service and confidence. Building from that foundation, it is important to distinguish between recovery and full reconstitution. Recovery refers to restoring system functionality quickly enough to meet mission needs, often through temporary means. Reconstitution, on the other hand, goes further. It rebuilds the system to its original or improved state, verified as clean and complete. For example, an organization may recover an email service within hours using alternate servers, but full reconstitution later ensures that every file, configuration, and patch level matches baseline standards. The difference lies in assurance. Recovery restores operations. Reconstitution restores integrity. Both are essential phases executed in sequence to balance urgency and confidence. From there, the process depends on clearly defined trigger conditions and decision authorities. A trigger condition describes what must occur before recovery or reconstitution begins, such as confirmed data loss, sustained outage, or detection of compromise. Decision authorities identify who can authorize these actions and who coordinates their execution. Without this clarity, teams may act prematurely or delay unnecessarily. For instance, if an intrusion is still active, beginning recovery could reintroduce risk. A predefined decision hierarchy, including alternates, ensures that choices are deliberate and traceable. These formal triggers prevent confusion and establish accountability in high-stress moments when speed must be balanced with control. Building upon those foundations, golden sources and integrity baselines provide the reference points for trustworthy rebuilding. A golden source is a verified copy of software, configurations, and data known to be free from tampering or corruption. Integrity baselines document the expected state, such as version numbers, approved hashes, and configuration settings, against which rebuilt systems are compared. For example, a golden image of an operating system, stored offline and verified through checksums, becomes the clean foundation for all new installations. Maintaining these baselines allows teams to detect unauthorized changes and confirm that restored components match approved states. Without golden sources, recovery risks reintroducing the very flaws it aims to eliminate. From there, the plan must establish a prioritized service restoration sequence. Not every system can or should come online at once. Dependencies between applications, databases, and authentication services require careful order. For instance, restoring a web portal before its database or identity service would yield errors and confusion. Prioritization ensures that supporting infrastructure, such as network, storage, and access control, returns first, followed by dependent systems. This hierarchy is usually based on mission criticality and recovery time objectives. Sequenced restoration turns recovery into an organized progression rather than a rush of simultaneous restarts that risk instability or data conflicts. Building on that sequence, teams must validate platforms before any data is restored. A clean operating environment is non-negotiable. Validation involves verifying patch levels, scanning for malware, and ensuring configurations align with baseline standards. Restoring data into an unverified platform can reinfect or corrupt the environment instantly. For example, if backup servers still carry remnants of malicious code, even verified data can become tainted upon import. Running vulnerability scans, checksum comparisons, and automated integrity checks confirms that systems are trustworthy. This step embodies the clean first, restore second principle that separates resilient recoveries from fragile ones. Extending that principle, credential resets and key rotations must accompany system recovery. Compromised credentials can silently undermine even the cleanest rebuild if reused without change. Resetting user and administrator passwords, regenerating encryption keys, and rotating service tokens eliminate potential backdoors. For example, after a ransomware incident, teams may reissue multi-factor tokens and revoke old digital certificates before reconnecting restored systems. This process ensures that any prior unauthorized access paths are closed. By treating identity and encryption artifacts as part of the recovery surface, organizations prevent attackers from regaining entry through leftover trust relationships. From there, the technical rebuild proceeds through re-imaging, reinstalling, and reconfiguring systems from code-based definitions. Infrastructure as code templates and automated configuration scripts provide repeatable, auditable processes that minimize human error. Re-imaging replaces potentially contaminated storage with verified golden images. Reinstalling ensures clean application binaries, and reconfiguring applies controlled settings from versioned repositories. For example, using deployment pipelines to recreate a web cluster ensures identical, approved configurations across all nodes. This approach not only restores functionality, but also modernizes security posture by enforcing consistency. Rebuilding from code transforms recovery from art into engineering. Building on that clean foundation, restoring data with verification hashes ensures that information integrity is preserved. Each dataset, whether a database, file share, or configuration archive, should carry a pre-computed hash value or digital signature. Comparing restored data to these hashes confirms that no tampering or corruption occurred during backup, transfer, or recovery. For instance, verifying database export hashes before import prevents contaminated records from entering the environment. Automated integrity validation reinforces trust in the restored state, ensuring that what returns online is exactly what was intended and nothing more. Data without verification remains untrustworthy, no matter how smoothly systems start. From there, parallel operations in a clean room or staging environment allow recovery teams to validate systems before reconnecting them to production. A clean room is an isolated segment where rebuilt systems operate temporarily for observation and testing. Running in parallel enables comparison between recovered and live environments, confirming correctness without risking wider disruption. For example, restored applications might process mirrored traffic until confidence is achieved. This method also supports forensic review, ensuring that no hidden malware or unauthorized changes persist. Parallel staging provides both safety and learning, revealing improvement opportunities before full reintegration. Building further, the cutover phase marks the controlled transition from recovery to full production operation. Smoke tests, quick, focused checks of system functionality, confirm that essential services perform as expected. Acceptance gates ensure that required approvals, test results, and validations are complete before the switch. For instance, a recovery manager might require signed verification that all databases passed integrity checks before lifting network isolation. Structured cutovers prevent premature declarations of success and provide a final checkpoint for assurance. When done correctly, the transition feels seamless to users while retaining full traceability for auditors and stakeholders. Extending past activation, post-restore monitoring ensures that systems remain stable and that regressions are detected early. Automated monitoring tools watch for performance anomalies, recurring errors, or reappearance of known indicators of compromise. Human oversight complements automation by verifying that business processes function as intended. For example, if system performance metrics deviate from baseline within hours of restoration, that signal may reveal incomplete remediation. Early detection prevents small residual issues from escalating into renewed outages. Post-restore monitoring confirms that recovery has not only occurred, but has endured. From there, documenting evidence of each recovery step, including timing, validation results, and approvals, turns execution into auditable assurance. Detailed records capture who performed which actions, when they occurred, and how success was verified. Screenshots, logs, and checklists provide tangible proof that the plan was followed and standards were met. This evidence supports internal reviews, external audits, and post-incident analysis. For example, time-stamped approval records show whether decisions aligned with established authorities and thresholds. Well-maintained documentation transforms recovery from a procedural act into a transparent, defensible process that reinforces organizational accountability. In closing, system recovery and reconstitution build the bridge between disruption and restored trust. The CP-10 control demonstrates that true resilience depends not just on restarting operations, but on doing so cleanly, verifiably, and securely. When teams rebuild from golden sources, validate every stage, and document results, they ensure that restored systems are stronger than before. Each recovery becomes both a restoration and a renewal, a proof that disciplined preparation yields dependable return. In that deliberate return to integrity lies the essence of trustworthy recovery every time. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.